Welcome to this video presentation by the postgraduate student whose poster it represents. We will miss the bustling crowds around the posters at the All Energy Conference this year, but we hope you enjoyed this online version that we have created. Before the presentation starts, I would like to acknowledge the support of our generous sponsors. Without this support, the competition could not proceed and the winning entrants would not receive a financial award. Our platinum sponsor is the Victorian Government through the Department of Environment, Land, Water and Planning. Its brands include Victorian Energy Compare, Victorian Energy Saver, Victorian Energy Upgrade Program, Energy Scorecard and Energy for Business. Their contact details are on the slide. Monash University's Monash Energy Institute is one of our silver sponsors. With over 170 staff involved, the Institute has a vision to bring people together to solve global energy problems. The Monash student posters in this competition represent some of that work. Baywa Renewable Energy is another silver sponsor. Baywa develops both wind and solar projects in Australia as part of a global energy portfolio. Baywa staff have also supported our AIE events in the past, including our Young Energy Professionals Speed Networking events. Our final silver sponsor is the University of Melbourne's Melbourne Energy Institute. Many of you will have attended their regular forums that keep the energy community and public up to date on technical and policy energy matters, and the University of Melbourne posters in this competition reflect some of that work. Seed Advisory is our bronze sponsor, and this small but well-recognised energy consultancy covers both the technical and regulatory fields. Seed Advisory has been a regular supporter of the AIE and a presenter at our events. Lastly, we thank All Energy for hosting our live poster events over the last decade, and we look forward to doing this again post-COVID. These last slides show you our poster winners in the last competition. And I now hand you over to the poster presentation. Thank you.
Thank you so much for your introduction, Glenn. First of all, I would like to thank Australian Institute of Energy and its sponsors for providing this great opportunity for all of us to present our research findings in the area of energy. My research group at the University of Melbourne has developed a novel technology associated with catalytic solvent regeneration for energy efficient CO2 capture. Herein, we show how this technology can take a determining step in the large-scale establishment of highly energy-efficient CO2 capture systems and pave the way for employing renewable energy resources for solvent regeneration. Considering Australia's climate change strategies and its responsibilities to meet international commitments, using low-temperature CO2 capture can be a viable strategy to control carbon dioxide emission in Australia and achieve the committed goals of Paris Agreement. Throughout the last century, global warming and its adverse impacts has been one of the major environmental challenges, which is mainly attributed to the consistent release of carbon dioxide from fossil fuel combustion. Since fossil fuels are expected to remain the predominant resources for energy production into the foreseeable future, post-combustion CO2 capture seems the only viable strategy to control carbon dioxide emission. Although chemical carbon dioxide absorption is considered as the most promising CO2 capture technology, the high operating temperature of carbon dioxide desorption process has resulted in a high CO2 capture cost and stopped its widespread implementation among the portfolio of low carbon energy technologies. A new technique for energy efficient solvent regeneration is using heterogeneous catalysts. In this technique, catalysts can enhance the desorption efficiency, promote carbon dioxide desorption rate, and decrease total energy consumption during solvent regeneration process. Apart from these benefits, catalyst addition also enables the solvent to achieve a regeneration temperature below 100 degrees Celsius rather than 140 degrees Celsius without using catalysts, which can be regarded as the main benefit of catalytic solvent regeneration. Here in the University of Melbourne, we have used a layer-by-layer technique for the self-assembly of different metal organic frameworks on the external surface of acidic Fe3O4 nanoparticles with superior texture properties and catalytic efficiencies. In this project, we coated 6 different metal organic frameworks with zinc, cobalt, iron, zirconium, and copper metal ions and succeeded to significantly reduce the required regeneration temperature to 88 degrees Celsius. The experimental results confirmed that all prepared nanocatalysts with different coatings can facilitate carbon dioxide desorption and reduce the amount of required energy. Interestingly, zirconium and copper-based coarser nanocatalysts displayed a distinguished performance during the regeneration of amine solution, resulting in 24 to 26% energy reduction. In addition, cyclic carbon dioxide absorption capacity improved up to 52.6% for zirconium-based nanocatalysts and 73.7% for copper-based nanocatalysts, which is considered a great achievement in the area of low-temperature carbon dioxide absorption-desorption. This technology has raised some promises to utilize solar hot water as the main renewable supply of heat for low-temperature regeneration operation, or act as the cooling tower to recycle the waste heat streams of energy power plants. Using solar hot water not only can decrease the operating costs of CO2 capture, but also can provide an incentive for coal-fired power stations in Australia to decrease the cost of electricity production and solidify their role in the global market. Therefore, in conclusion, this development can be considered as one of the most viable strategies to control carbon dioxide emission in Australia, achieve the committed goals of Paris Agreement, and pave the way for its transition to net zero emission and green energy production. Thank you.